Hello बच्चों, Sat Sri Akal and Namaste from my side. How are you all? Fine. Entire rotation will be divided into the two parts, right? Today's lecture is going to be quite not as large as compared to the previous one. It's not for 3 hours or 3.5 hours, something like that, right? But today's lecture is going to be right. Let's say I'm not telling you about the time, but we are going to discuss the center of mass from the basic to the top. Okay, we are going to discuss the center of mass from the basic to the top. The core concept of the center of mass, right? The NEET level sums, the main level sums, everything we are going to discuss, right? So, students, hello, Joe. Sat Sri Akal and Namaste from my side. So, students, this is your own physics educator Indrajit Singh welcoming you all onto the most important, right? Okay, session. Okay, for an aspirants, those who are preparing for JEE NEET kind of examination, center of mass. Without wasting our time, we are going to start. And again, those who are saying, like, heartily apologize for the teasers or something like that. I heartily apologize from my side. Things will get resolved in no time. Okay, we are on to it. Okay, we are on to it. So without wasting our time, we are directly moving forward for the concept of the center of mass. We are going to visualize it, we are going to imagine it, we are going to mathematically express it. Everything we are going to do into the next 1 hour 145 minutes of the lecture. Right? So shall we begin? Yes or no? Yes, we should. Okay, see, entire rotation is divided into two parts. The first I'm going to cover the center of mass, right? Actually with center of mass the collisions, right, okay, are always covered, but it's okay, we have covered this into the previous chapter of the right, work, energy and power. After this we have moved on to the moment of inertia, right? This will be the second lecture, okay, of the rotational motion, the second lecture of the rotational motion. Okay, lots of barish there, here, everywhere. Okay, entire South Gujarat, I live in South Gujarat, so entire South Gujarat is in red alert. Lots of okay, it happens, it's okay, it's a part of the life. Okay, because I thought you might be hearing the voice into the background of the rain, something like that. Actually it's raining, but it's okay. Okay, so the entire concentration would be right on the center of mass. Now let's move on to the right, the basic definition of the center of mass, what actually it states. Okay, if I am going to write down the definition first of all, okay, let's write it down and then we will discuss, right? Okay, so an imaginary point about which right, an imaginary point about which mass of system is concentrated. The syllabus is designed in a way. First chapter is a generalized introduction for the entire syllabus of the physics, that is units and measurement. In motion into the 1D, we are always dealing with the particle. We are not having any kind of the relation with the cause of the motion, and even we are not having any kind of the relation with the configuration of the object or particle. I'm not saying the particle is of the circular shape. I'm not saying it is a spherical shape. I'm not saying it is a block. I'm not saying it is a disk. Nothing is discussed because it's all about the kinematics. We are dealing without cause. Third chapter. And even it on the straight path, the rectilinear path. After that, when we moved on to the next chapter, that was motion into the 2D, we discussed everything same here. No configuration was discussed, no cause of the motion. Only we analyze the motion into the 2D part, into the 2 dimension. Slowly we reach to the NLM in which we deal with the cause of the motion. Yes, we deal with the cause. After that, we moved on to the work, energy and power. We will deal with the cause of the motion and its relevant energy. Okay, till 6th chapter, no of the internal configuration of the system was involved while analyzing the motion. But from now onwards, yes, the structural formation, right? The structural formation of the system is analyzed. Okay, the structural formation of the system is analyzed, right? How object is it spherical, right? Is it square? Okay, is it ring? Is it disc? How, if this kind of the objects having the structural formations are involved into the motion, how we are going to analyze it and what concepts are going to come upon it, right? What concepts are going to come upon it? Yes or no, guys? Yes or no? So what is the center of mass? See, I must say, right, before moving on to this chapter, at the very beginning, I'm going to tell you all that we are going to deal with the structural formation, right? So mark my words, right? We are going to deal with the awesome things, but you should be prepared of. Else, after reaching or after completing half of the chapter, suddenly, right, if you are posing a question, why these? Maximum number of the doubts, right, relies behind this statement. We are going to deal with the structural formation of the system and we are going to analyze the motion. Structural formation of the system and we are going to analyze the motion. Is it okay? Is it cool? Now, let's move on to the center of mass. Imaginary point about which the mass of the system is concentrated. I'm going to give you all one point. In entire system, there exists, right, a point. In entire system, right, please don't consider jai, please be serious. You are in physics class, right? Okay, please don't do like that. Please don't consider this way, jai. Please don't consider kya bol. Okay, we are going to understand the concept of center of mass through it, right? Okay, fun's apart. So mass of the entire system gets concentrated at an imaginary point. Mass of the entire system gets concentrated at this imaginary point. That imaginary point, it is nothing else but the center of mass. Please don't do like that also. Otherwise, students are having like that. Okay, please. You are in the physics class and I'm a physics teacher, right? I am a physics teacher. How dare you? So, let's take another example to understand the concept of the center of mass. This is a room in which you are sitting. The room is having the 6 faces. Yes, the room is having the 6 faces. Okay. The back wall, the front wall, the rear wall, front wall, top, there is ceiling and the floor and the left side and the right one. Okay. Now I'm picking the left wall. See, just imagine, focus on my words. The mass of the left wall is getting concentrated at the single point. It is shrinking. Mass of the left wall is here. Mass of the right wall is shrinking. Mass of the front wall is shrinking. Mass of the rear wall is shrinking to this point. Mass of the ceiling, mass of the floor. All of the masses of all of those walls are simultaneously shrinking at the specific point. This imaginary point, it is a center of mass. right? Imaginary point, in another sense, if you want to understand the point from which mass is equally distributed in all direction. This is not a technical definition, but is only for the understanding purpose, right? The technical definition is mass of entire system get concentrated at single point. So for that reason, I show you all, okay, that point can be here, that point be here, that point be at the mid, that can be that point can be anywhere. It can be inside the system, outside the system, right? Only mass of the system is getting concentrated at the single point. This is the center of mass. Okay, now we are going to discuss this thing into the detail. The first point is imaginary point. It is important to imagine. Why? Because the point is imaginary, right? It is important to imagine. Why? Because the point is imaginary. The imaginary point about which mass of the system is getting concentrated. Okay, now this point can be anywhere. Inside or outside the system. Point can be anywhere. It can be inside the system, it can be outside the system, right? Center of mass always, right, this point is always nearer to system, right, part having higher mass. For this second point, I'm going to give you all an example of it. Okay, center of mass point always shifts to the higher mass side. How? Right, let us take an example to understand this second point, and it is even important also. These 2 points, right, are important from the theoretical MCQs point of view. Many times the MCQs based on this are asked into an examination, right? The second point states, suppose this is mass m, right, and this is mass m. Okay, both are the identical masses. Obviously the center of mass, right, is and mass of the entire system get concentrated at the single point. So if I want to locate the center of mass, then it is at the midpoint. This is the center of mass of the 2 particles. But suppose if the giant particle is coming here, 3m, immediately this center of mass is gonna shift, right, towards the higher mass side. This will be the center of mass of system. Okay, I want to convey a very simple logic to you all. Center of mass point, it is an imaginary point. It always shifts toward the higher mass side. It is always shifts towards the higher mass side. The third most important point on which, right, there is a possibility for an MCQ to come up into an examination. Center of mass point, COM. COM stands for center of mass motion is not affected by the external forces. Sorry, internal forces. Right, center of mass. This third point we are going to discuss into the detail while dealing with the motion of the center of mass, right? For now onwards we are going to discuss, right, how to locate the center of mass for the n number of the applications. How we are going to locate the center of mass for the n number of the applications, that we are going to see. The classification of the center of mass. First of all, what is our main purpose for approximately, see, for next 30 to 45, more than 45 minutes, right? The purpose of this lecture would be to locate the position of COM. COM stands for center of mass. To locate the position for the center of mass. Okay. To locate the position of the center of mass. This is the next target. For this, we are having the specific classification. We are going to locate the center of mass into the right system formed by discrete particles. There are discrete particles forming the system. Right. We are going to see the center of mass for the continuous bodies. How to locate the position of the center of mass for the continuous bodies. Continuous bodies like ring, semicircular ring, sphere, hemisphere, solid hemisphere, right? Hollow hemisphere. Okay. This kind of the things we are going to see. We are going to locate the center of mass for the combined bodies and bodies with cavity. These three are the important things, and these three are having the respective formulas. Okay, if I am talking about the discrete particles forming the system, okay, here we are going to discuss randomly. Okay, after that we are going to discuss each and every part into the detail. Discrete particles forming the system, let's say, okay, in a Cartesian coordinate system, entire three-dimensional space, this is the particle of mass m1 having position vector r1. This is the particle of mass m2, right, having the position vector r2. This is the particle of mass m3, right, having position vector r3. Three masses, three particles. Now this individual, it is known as the discrete particle, and this discrete particle forms the system. Okay, this discrete particles combine to form this system. So in this case, we are going to use the general formula of center of mass into the vector form, that is m1r1. Here we are having the three particles like this. We can have the system of the discrete particle, the n number of the discrete particles. Right. So this is the formula for the center of mass. Now sometimes this direct formula is used, or sometimes individual x center of mass, individual y center of mass, individual z center of mass, right? They are calculated, okay, and they are finally they are going to combine to locate the center of mass of the system in three-dimensional space. For the continuous bodies, okay, for the continuous bodies, the center of mass, the r center of mass is equal to integration of r of dm whole divided by integration of dm. This r can be x, y or z depending on what excess mass is distributed. Okay, like this way it happens now, right? It happens now. Suppose this is a Cartesian coordinate system. This is x, this is y, this is z. This is a continuous body, right? Okay. Okay. Suppose it is distributed into the x-axis. So for this x center of mass, it is integration of x dm whole divided by integration of dm. Okay. What does the individual physical quantity tells, right, into the formula, what it conveys, right? We are going to discuss that into the detail. All of those things we are going to discuss into the detail, right? Now, if I'm talking about the third part for the combined bodies, let's say this is disk, another disk is kept. Okay, this is disk 1. Okay, this is disk 2, right? If these two are combined and this is their axis of rotation about which, right, they're going to perform the rotational motion. So for this also we are going to calculate the center of mass. And bodies with the cavities, right? Suppose we are having this square, right? Suppose we are having this square and this much part is cut. What is the center of mass of the remaining system? This kind of the applications we are going to see into this lecture, right? Okay, so this was just a formal introduction about the center of mass. So first of all, we discuss about the definition, right? And 3 of the important cases. What is the main purpose? To locate the position of the center of mass. Again and again, I'm telling you all, mark my words, to locate the position of center of mass. This is the stuff I'm doing all, right? What are the applications? Discrete particle systems we are going to see, continuous bodies we are going to see, combined bodies, right? And the bodies with the cavities. We are going to, for all of those applications, we are going to deal with the formula of the center of mass, and we are going to see the numerous, right, and number of the numericals with it, right, and number of the numericals with it. So are you all ready for it? Yes or no? Okay, so let's begin. So first we are going to see for the center of mass of the discrete particles, they form the system. Center of mass of the discrete particles, they are forming up the system. See, it's a very simple concept I'm talking about, right? Suppose this is a particle 1 having mass m1. This is particle 2 having mass m2. This is particle 3 having mass m3. What are its respective position vectors? See, this is let's say r3, right? Okay, this is r1. Okay, this is r2. Right? Yes or no? Okay. So here, these 3 discrete particles are combining to form the imaginary system. Okay. So center of mass for this is directly written as center of mass into the vector form, that is m1 r1 plus m2 r2 plus third particle, that is equal to m3 r3, right, whole divided by m1 plus m2 plus m3, right? Here r1, r2 and r3, if we are writing r1 vector into the 2D, then it can be x comma y, it can be y comma z, it can be z comma x. If we are writing into the 3D form, then it can be x comma y comma z. Okay. So these are the individual position vectors for the individual discrete particles. So you are having a 2 ways. First, directly you can reuse this formula, or individually you can calculate the x center of mass m2 x2 m3 x3 whole divided by m1 m2 m3. Individually you are going to calculate the y center of mass m2 y2 m3 y3 whole divided by m1 m2 m3. Individually you are going to calculate the z center of mass m1 z1 m2 z2 m3 z3 whole divided by m1 m2 m3. x1 is the x coordinate of the position vector of the m1. x2 is the x coordinate of the position vector of mass m2. Similarly, combining this, we are going to reach the center of mass as x center of mass, comma y center of mass, comma z center of mass. Or if you want to write it into the vector form, then it is x of I plus y of j plus z of k. Right? This is just a way of representing things. If you are having a very good practice, my suggestion is to use this formula, right, onto the very single shot. Why? Because this thing is only going to help you all, right, to increase your speed, okay, and accuracy. Right? Now, let's see some of the sums based on this formula. Right? Two particles of mass 5 kg and 10 kg. Some sums we are going to see. There are some PYQs also, and some of the nice sum we are going to see based on the formulas of the center of mass. of the discrete particles. Then we will move on to the continuous bodies, the combined bodies, and with their cavities. 5 kg and 10 kg are attached to the two ends of the rigid rod of the length 1 meter. See, this is the rigid rod. The length of the rigid rod is 1 meter. Two particles are attached to the opposite side. The particle 1 is having mass of 5 kg. The particle 2 that is attached to the another end, it is having the mass of 10 kg. The center of mass of this system, right? Okay, one important thing about the center of mass, right? That was important to discuss with you all. Okay, it is always calculated with respect to the reference point. It is always calculated with respect to the reference point. Yes or no? Always calculated with respect to the reference point. Right? So for that reason, in the very first question, it has been told, right? Calculate the center of, see, two particles attached to the two ends of the rigid rod of length 1. Here, see, negligible mass is given. Mass of the rod is negligible. It means we are not going to take it into the count. Right, so here we are having only two masses, m1, m2. With respect to this, it means this is going to be the reference point. This is going to be the reference point, and with respect to the reference point, right, okay, we are going to calculate the. See here, immediately by seeing this question, we are having a right thought. Which formula we want to use? Directly we are going to use the formula R center of mass, that is m1 r1, m2 r2, m3 r3, whole divided by m1, m2, m3. See, now in this case, all of those mass are distributed on the x-axis. So I can reframe this formula as x center of mass right, x center of mass, y center of mass, z center of mass, right, x center of mass, y center of mass, and z center of mass, right? Okay, so similarly the particles were distributed, so I did that. But here one thing is gonna get cancelled, m3 is gonna get cancelled. Why? The mass of the rod is negligible. Okay, so we are going to find the center of mass, that is m1 x1 plus m2 x2 whole divided by m1 plus m2. Okay, now mass 1 is 5 kg. What is x1? For discrete particle, x1 is the distance of particle with respect to the reference point. Distance of the particle with respect to m1, distance with respect to the reference point 0. m2 is 10 kg. What is the m2 distance with respect to the reference point? Right, m2 distance with respect to the reference point, how much it is? 1 meter. Okay, so whole divided by 15. So the center of mass position is going to be 10 by 15, 2 by 3 meter. Okay, 2 by 3 meter. So approximately it is going to be, right, 67 centimeter from the 5 kg. Okay, the 67 centimeter will be the perfect answer for this specific question. Okay, 67 centimeter is the perfect answer for this specific question. Yes or no? Okay. So I'm moving aside. If you want to just note this down, you can. Okay, on the countdown of, right, 5, 4, 3, 2, 1. This is a very simple sum, right? Immediately we're going to see 4 to 5 sums based on it, and directly we're going to jump off to the next part. 3 of the masses are placed on the x-axis. 300 gram at the origin. See now, directly using the data, we are going to apply and find out the equation. It is a system of the discrete particle. X center of mass, it is m1 x1, m2 x2, right? m3 x3 whole divided by m1, m2, m3. Okay, m1 x1, m2 x2, m3 x3 whole divided by m1 plus m2 plus m3. Right? So 300 gram is at origin. M1 is, see, origin will be our reference point. Okay, in heart I select origin is our reference point. 300. Oh yeah, everything is fine. So M1 I'm going to take it as a 300. So distance of the 300 with respect to the origin 0. Why? Because 300 is on origin only. 500 is at the 40 centimeter with respect to origin. So 500 into the 40 centimeter plus 400 is at the 70 centimeter. Okay. So here 400 into 70 whole divided by 300 plus 500 plus 400. Okay. So 5 into 4, 20,000 plus 28,000 whole divided 5384, 1200. So the position of the center of mass is going to be 48,000 whole divided by 1200. The 0 is going to get cancelled. 1240s are. The center of mass, it is going to be at the 40 centimeter. With respect to the reference point, it is calculated, right? So this is with respect to what reference point? With respect to origin. For this case, it is x is equal to 0. For this case, it is x is equal to 0. A is the perfect answer for this specific question, right? A is the perfect answer for this specific question. Yes or no, guys? Okay. A is the perfect. Now, let's move on to the next part. Two bodies of mass 1 kg and 3 kg have the position vectors this and this. The center of mass of the system has a position vector. Now see here, vector is involved. Generally, the reference point, we are taking it as an origin. Generally, the reference point, we are taking it as the origin. Okay, the reference point, we are taking it as an origin. So here, what is going to happen? Now here you are having the two choices. Either you want to, you can apply the center of mass formula directly into the vector form. Or if you want to miss that part, if you want to calculate x center of mass, y center of mass, z center of mass individually, then it is going to be the very long process. So I think it's good. Directly you can apply the formula into the vector form. Because all of those position vectors of the masses are given, right? All of those position vectors of the masses are given. So I think it's cool, right, to directly apply the formula of the center of mass. Okay, only two bodies are there. I'm sorry. Okay, only two bodies are there. Okay. Boom. What is mass 1? That is 1 kg. Vector I2, so it's 1, 2, 1. Second mass is 3 kg. What is the position vector? -3, -2, 1. Whole divided by 1 plus 3, 4. Right? Directly we can use this into the vector form so that we can solve this sum into the convenient manner. And it is going to save our time. So it is 1, 2, 1 plus, right, -9, -6, 3. 1 minus 9 whole divided by 4. Okay, whole divided by 4. 1 minus 9 minus 8. 2 minus 6 minus 4. 1 plus 3, 4, whole divided by 4. What is the position of the center of mass? Minus 2, comma, minus 1, comma 1. Minus 2, comma, minus 1, comma 1. A is the perfect answer for this specific question. A is the perfect answer for the specific question. Yes or no? Yes or no, guys? Right? I'm moving aside on the countdown of 10 seconds. If you want to, right, just note this down. You can. It's 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Boom, boom, boom. Center of mass for the rigid bodies. Right. We are having the respective formulas for the center of mass of the rigid bodies, right, or the continuous bodies. But before moving on to that, right, we need to understand the concept of mass densities, right? We needed to understand the concept of mass densities. It is important whenever you are dealing with the configuration of the system. Mass densities are important. Okay, the same charge densities are going to come up into the 12th syllabus. Basically, we are going to deal with the three type of mass density. The first one is a linear mass density. The general formula, how mass is distributed over entire length. If on 1 meter there is 1 kg, if on next 1 meter 1 kg, on the third 1 meter 1 kg, on the fourth 1 meter 1 kg, combining length 4 meter, mass 40 kg. This is an example. What? How mass is distributed, right, over length. Lambda is equal to mass per unit length, right? How lambda, right, is equal to mass per unit length. Okay, now see, this is also having the two cases. First, uniform mass distribution. Second one, non-uniform mass distribution. In uniform mass distribution, see, this is for the higher value of the change. For the smaller change, lambda is defined as dm by dx, right? For small values or small changes, right? For the smaller changes or the smaller distributions, lambda, that is equivalent to dm by dx. This is also having the two cases, the uniform mass distribution and the non-uniform mass distribution. This exists in all linear densities. Uniform mass distribution, it means lambda is constant. That is equal to dm by dx, or that is equal to mass per unit length. What does this uniform mass distribution means? If on the first 1 meter we are having 1 kg, then on the very next 1 meter we should have 1 kg. On the very third meter we should have 1 kg. On the very fourth meter we should have 1 kg. This is uniformly mass distributed over the specific length. So that uniform mass distribution tells us about the linear mass density to be constant. Uniform mass distribution has two words. The linear mass density as constant, right? Linear mass density as constant, or it is having the uniform mass distribution. What does the non-uniform mass distribution tells us about? Lambda is directly proportional to x. Lambda is directly proportional to x square. lambda is proportional to x to the power n, lambda is proportional to x square plus x, like this way. Mass is randomly distributed. Somewhere, see, I'm going to give. This is the case of the uniform mass distribution from this point to this point. It's a symmetric object. If I'm considering the entire object, then it is a non-uniform mass distribution. Somewhere mass is less, somewhere mass is more, somewhere mass is more, right? It is increasing like that way. Okay, so this is a natural difference between the uniform mass distribution and the non-uniform mass distribution. Okay, uniform mass distribution and the non-uniform mass distribution. Okay, uniform mass distribution and non-uniform mass distribution. Okay, so this was right, linear mass density is generally for 1D objects. For 2D we are having surface mass density. Sigma, mass spreaded over specific area. Linear mass density. Mass distributed over length. Surface mass density. Mass spreaded over area. For smaller value, it is also as dm by d of A. Volume mass density. Right. How mass is contained into the volume. Mass per unit volume for the smaller values, dm by dv. Okay, so these are the most important three type of the densities that we need to evaluate in. We are going to use this three type of the densities into the results. Okay, we are going to use this three type of the densities into the results, right, for the continuous bodies. See, if we are dealing with the continuous bodies, right, if we are dealing with the earth, then we need to take atmosphere into the consideration. If we are dealing with the space, then we need to take vacuum into the consideration. If we are taking, right, we are dealing with the concepts of moon, then we need to take g/6 as into the consideration. Similarly, whenever you are dealing with the configuration of the system, mass densities plays the pivot role, okay, in all of those concepts, and they are going to use here, you are going to use this concepts maximum into the all of these cases. Okay, so now let's move on to the center of mass for the rigid bodies. First of all, I'm going to give you all the example of the rigid bodies, and then we are going to discuss that part into the detail. Okay, what are the rigid or the continuous bodies that are having either it can be 1D, 2D or 3D? The rod is the rigid body. The ring, okay, generally practical, like into the practical life, rigid body kind of thing never exists, because rigid body means the mass of the the distance between the two particles never get changed. Okay, it means no forces are going to change the configuration of this rigid body, no temperature is going to change, no friction heat is going to change, neither it can melt, nothing. So practically concept of rigid body is not possible. Why the concept of rigid body is taken into the mechanics? Why the concept of rigid body is taken into the mechanics? Because we are at all of those point of time, we are going to deal with a different kind of the forces that may hamper or change the configuration of the system, right? That is a possibility. Okay, so to reduce that, okay, into the beginning part only, in the beginning part only, they have taken this as a assumption. Rigid body. Okay, disc is the rigid body. Okay, sphere is the rigid body. Hollow sphere is the rigid body. Cone is a rigid body. We are going to deal with all of those concepts and blah 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 blah. Lots of things we are going to discuss. Okay, so discrete particle is over. Now we are going to move forward to the, okay. See, before that, I think we need to discuss some of the examples with you all into the detail. So for that, I need extra slide. Okay, see, center of mass for the continuous body. How you are going to deal with that? What is the Brahmastra of it? How you are going to deal with that, and what is the actual Brahmastra of it? Yes or no, guys? How we are going to deal with that, and what is an actual Brahmastra of it? Okay. Sorry for the interruption. Okay. There was a text. Okay. So no worries. Yes. Continuous body. Suppose, first of all, let's take an example. This is disk. Let's take two axes. This is x-axis, this is y-axis, right? And the third one is the z-axis. Okay, x-axis, y-axis and z-axis. See, with respect to x-axis, fold the system. Mirror image is formed with respect to x-axis. Mirror image is formed with respect to x-axis. It means, first point, mirror image is formed with respect to x-axis. It means that, right, mass is equally distributed on either side. Mass is equally distributed on the either side with respect to x-axis. With respect to y-axis, mirror image is formed. So same happens with respect to y-axis. Same happens with respect to z-axis also. Right? Like this way. Okay. So from with respect to all of those axes, the mirror image is formed. The object that is on the left side of the axis is exactly same as the object on the right side of the axis. That is known as mirror image. So as of this reasons, right guys, as of this reasons, what happens here? As of this reasons, what happens here? The center of mass is exactly at the midpoint. The center of mass is exactly at the midpoint. Why? It is exactly at the origin or midpoint. The specific word would be the origin. Right? Why? Because with respect to all of those axes, the mirror images are formed. So that's why the center of mass. Suppose if with respect to any axis there is a slight change into the mass, the center of mass will be shifted towards the higher side. This thing we have seen into the very first presentation slide of this session. Center of mass shifts always towards the higher mass side. Here with respect to all of those axes, the mirror images are formed. The object that appears to the left side is exactly equivalent to the right side. Okay, so as of this reason, okay, as of this reason, what happens here? Okay, as of this reason, what happens here? Okay. Suppose with respect to any axis, slightly there is a change into the mass. Suppose, let's take an example. If I'm going to keep here the small object, okay, then immediately the center of mass is going to shift towards this side. This will be the new center of mass. This is the thing that I want to convey, that center of mass always shift towards the higher mass side. How I'm going to represent this, okay, into the very different manner. See, this is y-axis, this is x-axis, this is z-axis. I am talking about the semicircular disc. I am talking about the semicircular disc. The half of the part of the disc is cut. Now what happens here? With respect to y-axis, mirror image is formed. First point. If with respect to y-axis mirror image is formed, then no shift of center of mass occurs at x. With respect to y-axis it is formed na. Left side is equivalent to right side. So it means center of mass is not going to shift on either this side. If left side would be of the higher mass as compared to the y, then center of mass would be shifting to this position. If right side would be higher as compared to the left, then center of mass will shift on this position. But left is equivalent to right, left is equivalent to right, so center of mass is in between. But with respect to x-axis, no mirror image is formed. With respect to x-axis, no mirror image is formed. It means shift will occur on y. Center of mass shift will be on y-axis. Center of mass shift will be on the y-axis. Center of mass initially was at this position. This is the initial center of mass. Now it is going to shift to the higher mass side. This is the new center of mass. This is what I'm going to convey. I want to convey that center of mass always shift towards the higher mass side. If it is a full disk, it is at the center. Why? With respect to all of those three axes, mirror images are formed. But if half of the disk is cut as a cavity, right, then immediately it is going to shift towards the higher mass side. Whether it is going to shift towards the x-axis or y-axis, right, I'm going to tell you all again. See, let's summarize this. Whole disk, this is x-axis, this is y-axis. First example. This is the center of mass. Semicircular disk, this is y-axis, this is x-axis. This is the center of mass. It is always toward the higher mass side. Quarter part of the disk. Neither mirror image with respect to x-axis it is forming, nor mirror image with respect to the y-axis is forming. So this was the previous center of mass. Now this is going to be the new center of mass. It will shift from x-axis also, and it will shift with respect to y-axis also. Okay. Here, no shift. Okay, shift towards y. Shift on both. This logic we are going to use in dealing with the center of mass for the continuous bodies. Okay. See, center of mass of the continuous bodies are having the specific formulas into it. Center of mass of the continuous bodies are having the formulas, right? First of all, the important formula is this: x center of mass, it is equal to integration of x dm whole divided by integration of dm. Okay, we are going to use this formula. See, there are the derivations. Using this formulas, right? All, see, center of mass of the semicircular ring, it is going to come upon as 2r by pi. So this is obtained using this formula. Center of mass for the semicircular disc is going to come upon as 4r by 3 pi. This has been obtained using this formula. Center of mass for the hollow hemisphere, it is r by 2. This has been obtained using this formula, right? There is a derivation. Center of mass for the solid hemisphere, right? There is a derivation, okay, to reach up to this result using this formula. For hollow cone, for solid cone, for everything there is a derivation. But from the JEE point of view, from NEET point of view, the derivations are not going to come, right? So it is good. I'm going to show you all, right, some examples how to derive all of those results from this formula. I'm going to show you 1 or 2 examples, right? I am going to show you all 1 or 2 examples, right? But it's okay, we can say that. Okay, we can say that. Okay, so this is a formula that has been used. Okay, now we are going to identify the cases of the rod. Okay, we are going to identify the cases of the rod. Okay, so for that I need an extra slide. Okay, so let's begin with it. Okay, allow me to drink the water first, and now we are going to begin with it. Some students might be having a doubt that why this sort of thing is there, how to use this formula for the continuous bodies. I'm going to give you all an example. What are the each physical quantity in the formula, right? Notes. So let us take an example of the rod. The question states that I want to find the center of mass of the rod of length L. First case of uniform mass distribution, second case of non-uniform mass distribution. Suppose this is a rod of length L having uniform mass distribution. First case, right? For this kind of cases, first thing, center of mass is always calculated with respect to the reference point. This is the reference point. Okay, this is the reference point. Yes or no? Okay, this is the reference point. Now, for the continuous bodies, always a small elemental mass is needed. Let us take an example. The small elemental mass is this. It is dm, width is dx. It is at the x distance with respect to the reference point. Why? I have taken the elemental mass. There is always why and suppose. Why? So the thing is like that. Why? Continuous body can be of any type. It can be the circular or anything, right? In the universe, infinite number of the circular bodies with the infinite number of the configurations are present. Right? So for that, this small elemental mass is needed. The small elemental mass is always the straight line. And using this, we are going to integrate and reach up to the results. Suppose this small right elemental mass is needed. So it is dmx whole divided by integration of dm. What is an x? X is distance of elemental mass to the reference point. In all of those formulas, students always used to get confused into the value of x. They never understand what we need to take as an x. Now here the uniform mass distribution it is given. It means lambda is constant. Mass per unit length dm by dx. If it is constant, then and then these two terminologies are going to be equal, and we are going to reach up to the mass as dm, that is equal to mass per unit length into dx. Consider this as equation number 1. Okay, now we are directly using up this formula to reach up to the results. X center of mass, can we replace the formula of dm, that is m by l into dx dot x. Now here x is the distance between the elemental mass and the reference point. Here it itself is an x. Whole divided by integration of dm, that is m by l into dx. M by L is gonna get cancelled. Now what are the limits of the integration? Limits of the integration is the point from which x starts, the point from which it ends. Suppose if I am going to take the elemental mass to this point, the starting point of the rod, then x is 0. And if I am going to take to the extreme level, then x value is going to be L. So the limits will be from 0 to L, 0 to L. So x center of mass, it is going to be integration of x dx, integration of dx, right? 0 to L, 0 to L, right? So this is gonna be L by 2. It is going to come upon as an answer. So with respect to the reference point, we have located the position of the center of mass for the right rod, okay, having the uniform mass distribution, right, having the uniform mass distributed over the specific length. We did that part. Okay, we did that part. Now some students might be in a thought, sir, what is an example of the non-uniform mass distribution? Linear mass density varies as by this equation. At x, density is lambda 0. At L, density is lambda 0 L. Mass density varies from lambda 0 to lambda 0 L. It means it is a very simple case of non-uniform mass distribution. Non-uniform mass distribution. Again, same thing, we are going to take one elemental mass. This is at the distance x, right? This will be our reference point, x is equal to 0. We are going to take up the formula, integration of x dm whole divided by integration of dm. This is the position. We are going to locate the position for the center of mass. We are going to locate the position for the center of mass, yes or no? Right? Now what happens here? Okay, see now. Lambda is equal to dm by dx. I can't write it is equal to m by l, right? Because it is a non-uniform mass distribution. So from this, can we say that dm, that is equal to lambda into dx? Yes or no? Okay. Now we are going to replace into the equation to get the specific answer. X center of mass, that is integration of x dm whole divided by integration of dm. So this is equal to integration of lambda x dx whole divided by integration of lambda into dx. Now here lambda is not constant, so it means that lambda that depends on x we need to replace into the specific equation to reach up to the results. What will be the limits from 0 to L? Okay, so this is center of mass. It is going to be integration of lambda 0 x square dx whole divided by integration of lambda 0 x of dx. Lambda 0 is a constant value. Here lambda 0 is constant, so it is going to get cancelled. So we are going to get it as x cube by 3 into x square into 2, limiting from, right, 0 to L. Okay, so this x center of mass, it is going to come upon as 2L by 3. Right, from the reference point at the 2L by 3 distance, right, we are having the location of the center of mass. We are having the location of the center of mass. You can easily compare. Into the uniform mass distribution, it is exactly coming at the midpoint. Into the non-uniform mass distribution, see, mass is varying with respect to x. Density is increasing with respect to x. So it means mass is also increasing with respect to x. So see, from the midpoint, center of mass shifted towards the higher mass side. Okay, center of mass shifted towards the higher mass side. Yes or no? Right? Okay. Like this way, I'm going to give you all one homework. Right? That this is the reference point. Okay. Mass density varies as find the center of mass of this system of the rod having length L and the non-uniform mass distribution, and the mass distribution varies with this equation. Okay, so guys, this is a homework from my side and you have to answer this homework question beneath the video. Right, this is a homework from my side and you have to answer the homework question beneath the video. Okay, you have to answer the homework question beneath the video. Yes or no, everyone? Okay, is it cool? Now with this, right, we can have the center of mass for the semicircular ring. Right, what we are going to do, again we are going to take one elemental mass. This is the center. The elemental mass extends the angle of d phi. Mass is dm, width is dx, radius is r. Okay. We have selected, it's a ring, not disk, semicircular ring. Now, with respect to x-axis, mass is equally distributed, but with respect to y-axis, with respect to y-axis, mass is equally distributed. With respect to x-axis, mass is not equally distributed. So in this case, it is a case of the uniform mass distribution. Y center of mass, here it is going to shift towards the y. This will be the location of y center of mass that we need to calculate. Right, so that is equal to dmy whole divided by integration of dm. Y is the distance of the center of mass of the particle, or you can say the distance of the elemental mass with respect to what? Reference line. This is a reference line. This is the distance. Suppose if you want to calculate this as phi, right? Okay, this is 90, then this is going to be r sine of phi. Okay, so this y value is going to be r sine of phi. Okay, so consider this as equation number 1 now. Lambda is equal to dm by dx. Dm, that is equal to lambda dx. Okay, if I am going to apply the small formula of theta, this is d theta, this is dx, this is r, then d phi, that is equal to what? Angle is equal to arc upon radius, dx by r. So dx, can we say it as r d phi? Replace it here. Directly we are going to replace into the formula y, center of mass, that is equal to integration of dm into y. Right, dm is equal to lambda dx, that is r d of phi into y, that is r sine of phi, whole divided by integration of, that is dm, that is lambda r d of phi. What are the limits of this integration? This semicircular ring is subtending from 0 to 180. So what are the limits of this integration? Right, this elemental mass is changing its angle from 0 to 180. Here it is 0, 1 point, another point, and angle is 180 into the anti-clockwise direction. So the limits are 0 to pi, 0 to pi. One r is going to get cut, one lambda is going to get cut, right? Okay, so here you are going to get it as y center of mass is r, integration of sine phi d phi, whole divided by integration of d phi, limiting from 0 to pi, limiting from 0 to pi. So this y center of mass, it is going to come upon as 2r by pi. For semicircular ring, for the whole ring, it was at the center. For semicircular ring, it shifted up to the 2r by pi. This is how for the continuous body using these formulas, like the derivations are done. Now, like say example for disk, I'm moving aside if you want to just note this down. And I can understand at the very first point of moment it is difficult, right? Okay, but you can immediately move on for, right? You can just pause this video immediately. Okay, you can just pause this video immediately, right, to move on to this part, right? So this is how things are always gonna get measured, like this way, right? See, for rod, we selected the elemental mass dm. For ring, we selected the elemental mass. Similarly, for disk, now disk is of the 2D shape. For this, it is difficult to select one elemental mass. So in this case, right, the center of mass of the ring is known. As this we have seen into the previous case, the center of mass of the ring is known. So what we are going to take, right, we are going to take the elemental mass as the ring. The ring of the mass dm, right, okay, and the width dx, okay, and it's the center of mass of the ring, okay, of the radius x, it is going to be 2x by pi, okay. So the selection of the elemental mass into the continuous body plays a pivot role. Selection of the center of mass into the continuous body plays the pivot role. Okay, so guys, this is a homework from my side. If you want to, you can just try and answer this question. And apart from this, whatever the number of the datas are there, right, I have given all of those datas, right, for the hollow sphere and a solid sphere and like this. So this is all about the center of mass for the continuous bodies. Okay, now let's move on to the next topic, and that is the center of mass. How to locate the center of mass for the combined bodies. Okay, how to locate the center of mass for the combined bodies, and we are going to directly see. Okay, now see, from the fundamentals of the center of mass, only two things are remaining. That is center of mass for the combined bodies, right, and center of mass with the bodies with cavities. Okay, so this thing we are directly going to discuss into the form of sums, right, because now you are aware that what actual the sum is all about, right? Okay, now you are all are aware of, right, what actual the sum is all about, right? Okay, so directly we are going to move forward to the sums. I'm sorry, you have to just lock it up. Okay, directly we have to move forward towards the sum. See, now combined bodies. Let's say this is disk of the radius r. Another disk is kept in like this way. This is of the radius r by 2. Okay, two disks are there. One is of the radius r, second is of the radius r by 2. Right? Okay, what will be the center of mass of the new system? This is how the center of mass of the combined bodies needs to be calculated. Right? Center of mass of the combined bodies needs to be calculated. The simple formula we are going to use, right? X center of mass, that is m1 x1 plus m2 x2 whole divided by m1 plus m2. in this kind of cases, just see, check it out. By keeping this disk, this is x-axis, right? This is y-axis. See, fold the system with respect to x-axis, mass is equally distributed. Fold the system with respect to the x-axis, mass is equally distributed. If mass is equally distributed with respect to x, no shift on y. With respect to y, mass is not equally distributed. So it means that if no equal distribution with respect to y, there will be shift on x. Okay, there will be shift on x. But here in this case, masses are not given, only the radiuses are given. So first step, we have to reach up to the masses. How? Using the mass densities, right? Using the mass densities. See now, if I'm going to write for the larger disk, the mass is distributed over the specific area. So mass of the larger disk, that is equal to sigma into pi of r square, that is capital M. For the smaller disk, radius is r by 2. So smaller disk, that is sigma into pi r square by 4. Mass of larger disk will be m. Mass of smaller disk will be m by 4. We got the masses. Let's replace this into the formulas to get the specific results. X center of mass, that is m1, x1 plus m2, x2 whole divided by m1 plus m2. Right? Okay. See now. M1 is a mass of, center of mass is always calculated with the respect to the reference point. This origin will be the reference point. For the whole disk, see, I told you all into the previous case. What is x here? If it is a discrete particle, then it is a distance between discrete particle and reference point. But if it is the continuous body, then this x1 is the distance between center of mass of the continuous body and the reference line. x1 for particle, distance between particle and the reference point. For the discrete particles, for the continuous body, x1 is distance between center of mass of the reference point and the reference line. M 0 plus another m. This is the mass of the smaller disk is m by 4. Now what is the center of mass of the smaller disk lies at here. Distance between this and the reference line is of r by 2. So I'm writing it as r by 2 whole divided by m plus m by 4, that is 5m by 4. Okay. So this is going to be m by 4 into r by 2 whole divided by 5m by 4. M by 4 is going to get cancelled. R by 10 will be the center of mass of the system. From this, right, center of mass got shifted to r by 10, and this will be the new center of mass of system. New center of mass of the system. This is how the center of mass for the combined bodies are calculated. We are going to see some else sums also, don't get worried. Now let's move on to the next example onto it. Right? Mass 1 kg, mass 2 3 kg, mass of the rod 2 kg, length of the rod 4 meter. Right. So these are the combined bodies now. These are the combined bodies. So how we are going to calculate the center of mass? See, to calculate the center of mass, always the reference point is needed. Directly x center of mass, that is equal to m1 x1 plus m2 x2, right? Okay, see, there is a difference to calculate the value of x. For that reason, I've taken this example, because in this example, both, right, these particles and the system, the discrete particles and the continuous bodies, both are involved. So with this example, you will get in a perfect idea how to calculate the differences, right? How the distances differs into the continuous bodies and the discrete particles. So M1 is a continuous body. This is a reference line. 1 with reference line is 0. M2 is a rod. It is a continuous body, right? So for the continuous body, the x2 will be distance of the center of mass and the reference point. Mass is 2 kg. Distance, we are going to take it as 2 meter. Third, mass 3 kg, distance 4, whole divided by 1 plus 2 plus 3. So the x center of mass, it is going to be 4 plus 12 whole divided by 6, 16 by 6. X center of mass, it is going to be, right, 8 by 3. This is the perfect answer for this specific question. Right? This is the perfect answer for the specific question. Yes or no? So this is how the center of mass is calculated for the combined bodies. Okay. Now let's move on to the next example on it. Square disc and disc. Square and disc. Ground. The length of the square is L. Right? The length of the square is L. Right? Masses are not given. One reference point we need. You can take anything as a reference point. For ease of this calculation, I am taking this as a reference point. Right? I am taking this as the reference point. Okay, for ease of this calculation, right? Okay. So now, masses are not given. This radius is L by 2, right? So mass is equal to density into area, that is pi r square. Mass of the square, that is density into L square. Okay. So this is gonna be m by pi. If mass of disk is m, right? Okay. Or suppose, wait, here radius is L by 2 na, so sigma into pi, right, L square by 4, right? Okay, suppose if we are taking this as m, then this is gonna be mass of disk as m pi by 4, right? Sigma L square is m and this is gonna be m pi L, right, by 4. Now directly we are going to apply the formula with respect to the reference point, right? This time it is going to be y center of mass, because it is on the y-axis. This will come upon this reference line, na? Right? So it is m1 y1 plus m2 y2, right, whole divided by m1 plus m2. So this is going to be m1. m1 is going to be mass of the first, that is m. Distance y1, mass of 1, the center of mass of the first continuous body with respect to the reference, 0. Plus mass of second is L by 2 plus L by 2. So that is L. So m pi by 4 into L, whole divided by m plus m pi by 4. Okay. So this is going to be come upon as m pi by 4 into L, whole divided by pi plus 4 by 4 into m. M is going to get cancelled. So this is going to be pi L by pi plus 4. So from this, a distance of pi L plus pi by 4, this will be the new center of mass of the system. With respect to this L by 2 you are going to add it. L by 2 you are going to add. This is with respect to the center of mass of the square. Okay, I am writing with respect to the center of mass, okay, of the square. Right, with respect to the center of mass of the square. So this was all about the continuous body. Now let's move on to the center of mass for the bodies with cavities. Simple sums are there into the bodies, into the cavities, but it's okay. We are going to see that part. Dhumtana bodies with cavities. There is a disk of the radius r. From the disk is of the uniform mass distribution. This much part is cut as cavity. The question says, find the center of mass, the location of center of mass, right, of the remaining system. So in this kind of the question, the same formula we are going to use, but we are going to use into the different ways. Okay. First of all, I want to tell you in all of those cases, right? Okay. Only the radiuses are given, never the masses are never given. So on basis of the densities, first of all, we need to calculate the mass. Mass of the larger disk, that is equal to sigma into pi r square, is equal to m. Mass of the smaller disk, you can say mass of cavity, sigma into pi r square by 4, that is equal to m by 4. What is the mass of remaining system? Mass of total system minus mass of cavity, 3m by 4. On basis of this density, sigma into mass per unit area, on basis of this formula we calculated mass of whole disk, mass of cavity, mass of remaining system. Now what we are going to do? Right? What we are going to do? Same formula we are going to use. X center of mass is equal to m1 x1 plus m2 x2. The way is gonna be different. Why? Because we need to reach up to the answers into the less amount of the time, and the answer should be accurate. So for that reason, right, I am following the different approach. See, this is x-axis, this is y-axis. With after cavity is cut, with respect to x-axis, mirror images form. No shifting on y. With respect to y-axis, no mirror images form. There will be shifting on x. Center of mass. This is original center of mass. It will shift towards the right. This will be the new center of mass. Right? The new center of mass. Now, students always used to take M1 as larger disk minus M2 as a smaller disk. Then and then you are going to get the value of this concept arises. But I want to advise you all, please don't follow that stuff. Okay, just move on to the very simple approach. Consider this as a three-dimensional space. M1 as remaining, M2 as cavity, both combinedly form whole system, and for whole system center of mass comes at the origin. If M1 as mass of remaining system, M2 as mass of cavity, then it forms combinedly, it forms the whole system, and the center of mass of the whole system will come at 0, 0. This will ease your calculation, guys. How? 0, that is equal to M1 mass of remaining disk 3m by 4. What is the distance of the center of mass of the remaining disk with respect to the reference? Let's say it is x, we need to find it out. Plus mass of cavity m by 4, distance of the center of mass of the cavity with respect to the reference point is r by 2. Whole divided by m1 plus m2, it is going to be 0. Here x is going to get it as negative of r by 6. With respect to the origin, center of mass shifts toward the r by 6 on the left side. It shifts on r by 6 towards the left side. Yes or no? It shifts on r by 6 towards the left side. Yes or no, guys? Yes or no? Suppose if you want to, I am going to give you all the homework, one homework from the question under the right cavity. This is a square base cavity. This is y-axis. This is x-axis. A semicircular cavity is cut from it. Right. The length of the square is L. The semicircular cavity is cut from it. My question, my homework to you all is, find the center of mass of remaining system. Right? Okay. Now, motion of the center of mass. It's a very important thing. Right? Till now, we have located the center of mass. But this time we are going to understand the motion of the center of mass. We are having the visualizations in front. Suppose, let's take an example to understand. Suppose this is a ring kind of structure. Two beads are kept. Right. One is of mass m, second is of mass m. What will be the, see, till now we have seen the location, right? We located the center of mass, right? Now we are going to understand the motion of center of mass. Till now we have understood, right, the concept of center of mass. Now we are going to understand the motion, whether the center of mass is moving or not. Right, let's analyze the simple example. This is M. This is M. Center of mass is at the midpoint. This is M. This is M. Center of mass is at the midpoint. Okay, now see, suppose. Just, you can just imagine, huh? Center of mass is moving or not. If both of the hands, right, are moving into the opposite side with the equal velocities, right, the center of mass will remain at stationary at that point. Right. Now, let us take another example. This is M. This is M. Center of mass is at the midpoint. Right. Now, only this particle is moving with a velocity v. You can just imagine the center of mass is also moving towards the right side. That's the motion of center of mass. Suppose this is m, right, and this is the center of mass. Now this is moving. You can just imagine the center of mass is moving towards the left side. Let us take another example. Right, this is m, center of mass is at the midpoint. Okay, now this is moving with v and this is moving with 2v, or this is moving with v, this is moving with 2v, right? Okay, so this is moving with v, right? Then also you can see the center of mass is moving, but towards the particle that is having higher velocity. Location of the center of mass is towards the higher mass side. Similarly, the velocity of the center of mass is always towards the particle that is having the higher velocity or higher mv, right? Okay, so it means yes, the center of mass is moving. Let's have another example. Bit of mass m, another bit of the mass m. See, this is the center of mass. Suppose the motion is starting at t is equal to 0. After some time, one bit is reaching here, second bit is reaching here. What will be the right? What will be the position of the center of mass at time t1? This is a new position. At time t2, particle is at here, this is at here. What will be the new position? At t is equal to 0, center of mass was here, and then it became here, then it here. Now, at t3, m is here and m is here. Center of mass. See, center of mass is going to be at the midpoint. Finally, we are going to reach here mm. Center of mass will be here, and they will just interact. Center of masses. What path the center of mass followed? Straight line. In between initial and final points, did we saw any kind? Did we found any kind of the motion of the center of mass? Yes. It was along the straight line. It was along the straight line. Now let's take another example to understand this stuff into the detail. Right now. Mass m, mass m. Both are scrolling down with the velocity. What is an initial position of the center of mass? Suppose after some time mass is here, position is here. After some time m is here, position is here. After some time m is here, right, m is here at the different time intervals, right? Position of the center of mass is here. So at the final stage m is here and m is here, position is. So in between t is equal to 0 to t is equal to time t, when journey is completed, whether center of mass moved or not? Yes. It gained some velocity? Yes, it gained some velocity. What path it followed? Straight line. Formula of the center of mass is R center of mass, that is m1 r1 plus dot 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 plus mn rn, right, whole divided by m1 plus dot 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 plus mn. Differentiating this equation, right, with respect to time, right, we get velocity of the center of mass, and that is m1 v1, right, plus dot 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 plus mn, right, vn, whole divided by m1 plus dot 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 plus mn. This is what the velocity of the center of mass is. If it is constant, I'm sorry, it is constant, right? It is constant. I'm sorry. Okay. Suppose in the previous case, in this case, it's not a big deal, right? These cases were just to tell you all, just to make you all imagine that yes, there is the motion of center of mass, right? whether the particles are getting accelerated or not, it is also important. Here in this case, particles are only having the different velocities, right? Velocities of all particles are constant. So that's why we are getting the constant value of the velocities of center of. But let's differentiate again with respect to time. We are getting the acceleration of center of mass as m1a1 plus dot 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 plus mnan, right, whole divided by m1 plus dot 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 plus mn. This is the acceleration of the center of mass. This is the equation of the velocity of the center of mass. M center of mass is at the midpoint. It is moving with the constant velocities, right? Then the things will get limited up to this equation. Suppose any one of them particles are getting accelerated, then the center of mass will also get accelerated. So basically, we have dealt with the two kind of motions, right? We have dealt with the two kind of the motions. The first one, a uniform motion in which the velocity of the particle is getting constant. It's a simple, na? Velocity of the center of mass is constant, right? If the velocity of the center of mass is constant, can we say the center of mass is performing the uniform motion? If velocity of the center of mass is either increasing, right, or it is decreasing, or in another sense, acceleration of center of mass is constant, right? So can I say the center of mass is performing, right, a uniformly accelerated motion? Right, uniformly accelerated motion. We are going to see all of those examples also. Don't get so much worried, just understand this concept. Suppose acceleration of the center of mass is constant. Yes, we can use this equation. What? S center of mass is equal to initial velocity of center of mass plus half the three equations of motion. V center of mass is equal to U center of mass plus A center of mass into T. Final velocity of center of mass minus initial velocity of center of mass is equal to 2 A center of mass and distance covered by center of mass. This is what actual the motion of the center of mass is, right? This is what actual the motion of center of mass is. To understand the motion of the center of mass, it is important to understand how to locate it, right? Okay, I think 1.5 hours of the lecture has been gone in this concept. Okay, still there are some things, right? After this we are going to discuss moment of inertia. Okay, but there are some things. Okay, see now, let's see the sums related to it. Some sums. Suppose, very simple, m1 that is moving with 5 kg, this is of 5 kg, m2 that is of 10 kg, right? This is having the v1 as 10 of I meter per second, and this is as v2 that is equal to negative of 10 of I meter per second. What will be the velocity of center of mass? These are the direct formula based question, that is m1 v1 m2, right, v2 vector whole divided by m1 plus m2. You have to consider the sign conventions in it, right? So it is 5 into 10, right, minus 10 into 10, right, whole divided by 15. So this will be 50 minus 100 minus 50 by 15, right? Okay, so 5 tens are 5 threes are, it's minus 10 by 3 I meter per second. What is the velocity of center of mass? Right, it's minus 10 by 3 of I meter per second. These are direct formula based question. Accelerations are given, right? Velocities are given. This is the velocity in 1D. The vector is in 1D. Okay, sometimes 2D equation is given, 3D equation, and lots of things are given, right? Suppose if I'm going to give the acceleration of this, then you are going to apply the direct formula of the acceleration. That acceleration of center of mass is m1 a1 plus dot 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 mn an, right, whole divided by m1 plus dot 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 mn, and you are going to get the answer. But things are getting changed, right, when new concepts are introduced. Suppose in this, right, you are going to understand, right, the concept of center of motion or the center of mass into the more appropriate manner. Suppose this is of 4 kg, right? This is of 6 kg. Initially, they are at the same level. Question states that in t is equal to 3 seconds, what will be the distance covered by center of mass? Nice question. Now, suppose this is 4 kg, this is 6 kg. We are completely aware of this 6 kg is going to accelerate with the net acceleration into the downward direction, and that is going to accelerate with the net acceleration into the upward direction. Right, and we are going to calculate the net acceleration. We are having the direct formulas also, or with this kind of the sums we have seen into the NLM. That is 6 minus 4 by 10 into 10, right? So the net acceleration is 2 meter per second square, right? Or you can take it as g by 5, right? Now, this is 4 kg. It is moving downward, sorry. This is 4 kg, right, and it is moving upward with the acceleration g by 5. This is 6 kg, right, and it is moving downward with the acceleration g by 5. What will be the acceleration of center of mass? It's very simple. Acceleration of the center of mass is, right, m1 a1, okay, m1 a1 plus m2 a2. It's m1 a1 vector, right, plus m2, right, a2 vector whole divided by m1 plus m2, right? What is mass 1? 4. Acceleration is 2 plus mass 6. Now, if you want to take upward as positive, according to the convention, we are taking upward as a positive and downward as negative, right? So 6 into minus 2 whole divided by 10. So 4 2s are 8, right, minus 12 by 10. So it's minus 4 by 10, right? It's minus 2 by 5. The acceleration of the center of mass into the vector form is minus 2 by 5 of j into meter per second square, right? We got that now. Whether the motion of the center of mass is this, right, the acceleration is constant or not. See, acceleration is not there, center of mass is performing the uniform motion. Acceleration is there, it is a case of the uniformly accelerated motion, right? So if you want to calculate the displacement, it means you need to use this formula. We got the acceleration of center of mass. Yes, we got that. What we need to calculate in 3 seconds, how much distance it is covered. So displacement takes displacement of the center of mass, that is initial velocity of center of mass of t plus half acceleration of center of mass into the t square. This same equation we are going to take into the vector form. Initially, when they both were at the same level, the system was at the rest. This part is 0. So the displacement vector, it is half. Acceleration vector is 2 by 5. Right, into t square. T square, it is 9. Okay, it's negative of j. So what is the displacement? What it states, the displacement vector state 2 is going to cancel. That is negative of 9 by 5, right? Okay, negative of 9 by 5. Okay, this is what the displacement, right? This is negative of 9 by 5 j meter per second. Sorry, only meter, right? It's only meter. Okay. This is the displacement. Magnitude of the displacement is distance, right? Magnitude of the displacement is distance. So distance is 9 by 5 meter. This is the distance traveled by the center of mass into the 3 seconds. If I want to confuse you all, right? If I want to confuse you all, (6 kg, 4 kg. Calculate the acceleration of the center of mass, and in 1 second, how much distance is it getting traveled? Simple. Net acceleration, it is in downward direction. Here the net acceleration into the right side according to the Newton's law. Right, from this we are getting the equation 6a is equal to 6g minus t, and here we are having 4a, that is equal to t. Right, so 10a, that is equal to 6g. So a is equal to 6g by 10. Right, so it is 3g by 5. Now obviously it is going to 6 meter per second square. Right, okay. This t is gonna cancel. Now acceleration of the first particle, it is in downward direction, so it will be negative of 6 of j meter per second square. Acceleration of the second particle is towards the right, so it is positive of 6 of I meter per second square. In this we are going to get the acceleration of center of mass m1a1 m2a2 into the vector form whole divided by m1 plus n2. m1 is 6 into 6 of I plus 6 into negative 6 of j and 4 into 6 of I whole divided by 10. Right, so we are going to get it as negative 36, right, of j, okay, plus 24 of I whole divided by 10. So it is equal to negative 3.6 of j plus 2.4 of I. This is of the acceleration of the center of masses. This is also constant, but in the previous case, I'm sorry, yaar, it is gone. It was a black screen. In the previous case, we were having that in 1D. In this case, we are having into 2D. So what will be the acceleration of center of mass is negative of 3.6 of j plus 2.4 of I. In 1 second, right? The displacement vector, initial velocity is 0, it's half, right? Negative of 3.6 plus 2.4 j plus I into t square is 1, right? So the displacement vector we are getting it as 1.2 of I minus 1.8 of j. This is the displacement vector for the center of mass. Magnitude of this, right, is a distance, right? That is 1.2 square plus 1.8 whole square. So this is how the motion of the center of mass is analyzed, right? Motion center of mass is always having the motion as because of the external forces, not as because of the internal forces. Center of mass is always having the motion as because of the external forces, not as because of the internal forces, always. Right? For internal forces, we are not going to discuss that much part, right? You all are aware of this example, right? Okay, first I want to write down the statement, right? The motion as of internal forces, the state of rest or state of motion of center of mass COM is not going to change. As of the internal forces, the state of the center of mass is never going to change. Let's take an example of it. You all are aware of this. This is a rod, right? And a man is standing at one edge. Rod is of length L, mass of man is M. Right? Suppose it is going on from this position to this position. Suppose a man is moving from A to B. What is the displacement of Planck? Right. But man is moving, right, it is getting displaced with respect to Planck. Right. So we are having mass of man, that is m1 plus m2, that is displacement of man with respect to Planck. Suppose he is moving with velocity v with respect to Planck. Let's differentiate this equation with respect to time. We get velocity of a Planck, that is m1 whole divided by m1 plus m2. V relative, again differentiating. Suppose the person is getting accelerated, so the acceleration of the Planck, right, that is m1 whole divided by m1 plus m2, right, A relative. This is all thing you all are aware of, right? Just keep one thing into the mind here, what actual the concept is, right? What actual the concept is. The concept states that, right, as of the internal forces, right, the center of mass is not going to change. See, suppose person was standing here. This is the center of mass of the rod. This is the center of mass of system. If the person is, let us take an example, person stands, okay, person is moving towards the left side, so obviously the Planck is going to displace. Suppose if the person reaches the right side, this is a C. You can just check it out. Center of mass, the initial position of the center of mass of the system, the final position of the center of mass of the system, right? It is same. It is lying on the same line. Why? Person who is running on the Planck, it is not applying the external force. I'm talking about the entire system, external force is 0. So whenever the external force is 0, center of mass is not going to displace if it at rest. And if it is in motion, it is not going to change its state. It's very simple. If external force on system is 0, net external force, center of mass is not going to change. This state. Let's see questions on this. Okay, see, the question on this concept has been asked in 2012. Two persons of mass 55 kg and 65 kg are at the opposite end of the boat. There is one boat, right? Okay, this is, here it is a person of 55 kg, right? And here the person is standing for 65 kg, right? Okay, the Planck weighs 100 kg. Planck weighs 100 kg. Now both are moving, right, nearer to each other. If boat is in still water, the center of the mass shifts by. Boat is in still water, external, the net external force on the system is 0. Whether the center of mass is going to shift of this system? No. Correct answer is 0. Students, this was all about right, the center of mass. As I told you all, the entire chapter is divided into the two parts. The first one is the center of mass, right, and second is a complete part of the rotation, in which moment of inertia, torque, the conservation of angular momentum, and all of those stuff, right, are going to come. Okay guys, so I think it's time to go. Thanks a lot. I will be waiting for all of your feedbacks regarding this video beneath, right, beneath into the comments. Thanks a lot for your cooperation and your time. Thanks for this, right, response into the victory badge. Okay, so this is Indrajit Singh signing off from the desk. Bachcha ji, bye bye, Sat Sri Akal and namaste from my side. Bye everyone. Stay at home, stay safe, stay healthy amidst this pandemic. Bye Chaji.